Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready to go?
Hello, it's Mr. T with another math tutorial. Today we're talking about a new family of functions called the logarithmic functions, or log functions. Log functions are the inverse functions of exponential functions that we've just studied recently. In the next slide, we'll better understand the relationship between the two functions. But remember, inverse functions undo something. So if we were trying to undo, say, x squared, remember we take the square root of both sides of the equation. If we're trying to undo x to the fourth, we would take the fourth root of both sides. So taking the square root or the nth root is the inverse operation of squaring or raising to the nth power. So in this case, when we have an exponential function, if we are trying to solve for x, we will be taking the log of both sides of the equation. Since when we raise a base to a power, we always get a positive number, then the inputs to a log function must be a positive number. So the domain of a log function are positive numbers. You can't take the log of 0 and you can't take the log of a negative number. One of the most important things that you can understand to help you comprehend what logarithms mean is to understand this relationship. So we have an exponential function over here and the equivalent log function. So just remember, I've kind of color-coded here, but the base of an exponential function is the base of a log function. We read this as log base b of x. So log function is not a single function, it's a whole family of functions. It could be log base 2, log base 5, log base 0.3, log base e, log base 10, etc. So the base of a log is equivalent to the base of an exponential function. And notice here the x switches places and the y switches places. We'll practice doing converting between the two forms in a minute. But what you can see by transforming a log equation into the exponential function, when we say take the log of base b of something, what we are trying to determine is what power would I raise this base to equal this value. So for example, if I was trying to evaluate the log base 2 of 8, for example, what that's asking is 2 to what power equals 8. So we know that would be 3. 2 cubed is 8. So the log base 2 of 8 equals 3. If we tried, say, log base 4 of 2, we would be asking 4 to what power equals 2. And that would be the square root, which is 1/2. So our value would be 1/2. So log base 4 of 2 is 1/2, because 4 to the 1/2 equals 2. Understanding this relationship between exponential functions, which most of you have a good understanding of, and log functions will take the mystery out of these log functions. Now, there are two commonly used logarithms: log base 10, which is referred to as the common log, and it's abbreviated by log without a base. So when you see log with no number here, no little subscript, that means it's a base 10. And also another common logarithm is log to base e. Remember the natural number that we used in our series on exponential functions. So log base e of x is abbreviated by ln of x. Now when we use calculators, there's a button for calculating the natural log and the regular logarithm, or the base 10 logarithm. There are not buttons to calculate the other logarithms, and we're going to be talking in the next slide about how we would do that. To calculate a log of some other base using a calculator, we have to use one of these two change of base formulas. So there's really two formulas here. You can use either one. So log base b of a is the natural log of a divided by the natural log of b, or it's the common log of a divided by the common log of b. So let's look at that to do a couple examples here. So for this, we could calculate the ln, or natural log of 5, divided by the natural log of 2. And using the calculator, so we've got here natural log of 5 divided by natural log of 2, and we get 2.32 if I round it. Now remember, that's saying, if we go back to logarithms, 2 to the 2.32 power is approximately 5. Now I put approximately here because I rounded that number. Now, we could have used this version of the form, so if I go and calculate base 10 log of 5 divided by the base 10 log of 2, I'm going to get the same number. So let's just show that we get the same. So log base 5, not base 5, log of 5 divided by the base 10 log, or the common log of 2, and we get the exact same number. So you can use whatever one you want. I wouldn't necessarily worry about both. Some calculators have buttons in different places, so some calculators getting the ln button is easier than the log button. On the graphing calculator, they're both easy to get. So on this one, we would be doing, say, the log of 5/16 divided by the log of 9. So let's see what we would get for that. So log 5/16. And to make sure you just, when you're using calculator, make sure you close that parentheses before you hit the divide symbol, otherwise you'll get the wrong number. So here we get negative 0.529. One of the things you would understand as we work with logs for a while, if you take the log of a number that's smaller than the base here, you're going to get a negative number. And when we take logs of numbers bigger than the base, we are going to get positive numbers. Now, one of the applications of logarithms is to what's said to be to compress data. So let's evaluate this column here. So the log base 10 of 1, again, that's asking 10 to what power equals 1, so that's going to be 0. 10 to what power equals 10 would be 1. This is going to be 3, and this is going to be 6. So you can see by taking the logarithm of this range of numbers that went from 1 to 1,000,000, we got a range of numbers from 0 to 6. So if we were trying to draw a graph of x values in this range, or y values in this range, if we graphed instead the logarithms of those numbers, we would have a much smaller range of numbers. Now we could also use the natural logs. Now I can't do those so much in my head. Now the natural log of 1 is 0, but the natural log of 10 is about 2.3. Natural log of 1,000 is 6.9, 6.91 say, and the natural log of 1,000,000 is 13.8. But again, the key thing is we're taking numbers that go from 1 to 1,000,000, so 6 orders of magnitude, and we are putting them into a range of about 1 power of 10. Now this property of logarithms gets used frequently in a lot of measurements that we use. So when you've read in the news or heard on the TV news about earthquakes that have happened in various places, they talk about the strength of the earthquakes using a number which is between, I don't know, it's always less than 10, so they're in the range of like 3, 4, 5, 6, 7. 7 would be a really big earthquake. This Richter scale is measuring the intensity or the amount of power in an earthquake, and those range of numbers would be quite large. So we use logarithms of the actual intensity for reporting, so it makes the numbers easier to understand. When we measure noise, we use something called decibels, and those also are calculated with a logarithmic scale. And also here, some of you have had chemistry class and you've measured the strength of an acid or a base using the pH scale. Remember that goes from, I think, 0 to 14. And any of you that are into astronomy, we talk about how bright a star is using its apparent magnitude. The key thing to keep in mind on these things is that they are logarithms. So if you hear of, say, an earthquake that was on the Richter scale of 4 and another earthquake of 5, that maybe doesn't sound like a big difference, but the earthquake of Richter 5 is 10 times more powerful than the one that was magnitude 4. So it makes the numbers easy to understand, but then it can be misleading in terms of small changes in these scales can mean quite large actual results. Now, when we're going to be working with logarithms, just as when we worked with exponents, we're going to have a series of properties of logarithms. Now, these properties all apply whether our base of the logarithm is base 10, so logs, or any other base. I wrote it here just for simplicity using the ln function, the natural log base e. So the log of any base of 1 is 0. Again, that's because any number raised to what power equals 1, and that would be that the question would equal 0. So the log of any of 1, no matter what the base is going to be 0. The log of a base is 1, so the more general thing of this is log, whoops. So the more general form of this is log base b of b equals 1. So that's kind of important. So if we took the log of 10, it would be 1. If we took log base 2 of 2, it would be 1. And the log of a base to a power, this would be base b here, is going to be x. So doing a logarithm undoes the exponential function. So these are some important properties to know. Also, if we take the log of a product, we could take the product and then take the logarithm, or we can take the log of each number separately, the x and the y, and then add them together. So log of a multiplication turns into a sum of logs. Log of a fraction or a ratio is the difference of the two logs. And essentially an extension of this property is if we have a log of some number with an exponent, the exponent comes to the front. Now, when we're working with logarithms, sometimes we have a log of maybe a more complicated expression, and we want to what's called expand it into multiple logarithms, but the logarithm of simpler things. For solving exponential equations, the first method we're going to use is we want to get the part of the expression that has the exponent by itself. And then we will take the log. Now we can use the natural log or we could use the base 10 log. It doesn't matter, of both sides of the equation. And we'll use our log properties to simplify our expression and then solve for x. So I have one all worked out here, and then we'll work one together. So this would be our original problem here. So we want to get the e to the u, meaning the base to the u by itself. So I have to subtract 10 from both sides. So now I have this. So now I take the logarithm of both sides. Now in this case, it will definitely be easier to take the natural log. So if the base is e, use the natural log. If the base is 10, use the common log. If the base is some other base, then it doesn't matter which log we use. Now on this side, we can use our log properties to bring the exponent in front. And we can also use the logarithm property that the ln of e is 1. So we end up on the left side with 0.1x. So notice by taking the ln of both sides, what we were able to do by this logarithm property we learned in the last video, we're able to get the x out of being an exponent and be a regular, in this case, linear variable. So now we just have to solve for x by dividing by 0.1. And then we can pull out our calculator and calculate the ln of 4 divided by 0.1, which is also 10 times the ln of 4. We didn't have to do this step here. And we get 13.86. Approximately, it's rounded. So if we put that number back into our original equation, it would check out. So let's look at another example. So we have one here. So we are going to get the expression with the exponent by itself. So I'm going to subtract 4 from both sides. Uh, 17. And now I'm going to log both sides. It doesn't matter which log we use here. And now we can use our exponent property to bring our exponent into the front. Times the log of 5. Now I need to get rid of this so I can divide by the log of 5 on both sides. And for most of you, you probably would want to go ahead and calculate that, and let's turn that into a decimal number here. So we've got here the log of 17 divided by the log of 5. So we have approximately 1.760. And now I would need to solve for x, so we're going to add 3. And then divide by 2. So again, I added 3. And now I'm going to divide by 2. And we get x is approximately 2.38. So again, if we put that number back into our original equation, it should check out. Now, an alternative approach here, instead of logging both sides, is to convert our exponential function to a log function. So remember, if we write this as a log expression, the log will be base 5. And remember, the 17 and this expression will change places. So this would be the log base 5 of 17 equals 2x minus 3. And to calculate this, we would have to use our change of base formula that we learned in the first unit. And that is precisely what we had at this point once we divided. So we had here 2x minus 3 equals that, and then we solved. So again, we can take the log of both sides, or we can transform our exponential equation into a log expression. Now, another way of solving a different type of exponential functions is when we have exponential functions on both sides of the equation. Now, this method that we're going to do will only work when these two bases are powers of the same number. In this case, both of these are powers of 2. So we need to convert both sides to have the same base. So 4 is 2 squared, and that's raised to the 3x power. And 8 is 2 cubed, and that's raised to the x plus 1 power. Now we can use the exponent rules that we learned in our last unit, so we're going to multiply those exponents. So 2 to the 6x equals, and here we've got to multiply 3 times that whole expression. And now, if we have two things that have the same bases that are equal, then that means the exponents must be equal. So we can equate the exponents. And now we can solve for x. And we get x equals 1. So again, this technique works when we have exponents on both sides of the equation. But again, these numbers for this method to work have to be powers of the same base. Okay, so that's it for, let's see, I have an application problem here for solving exponential equations. So we did compound interest back when we did exponential functions. So we want to double our money. So it didn't tell us what our initial investment is. So we'll just use letters here. So our initial investment, so remember we're using this model for continuously compounded interest. But in this particular problem, we know, or we were told, that we want this amount to be double what we deposited. So 2p would be double what we deposited, and we were told that the interest rate was 0.08, and we want to solve that for t. So we have a exponential function, so we want to get the exponential part by itself. So that gives us this exponential equation. Now we could either log both sides, or we can rewrite it as a exponential function. So let's take the logarithm of both sides. So we'll take the natural log of both sides. Now using our logarithm properties, the log of a base to a power just gives us that exponent. So the ln of 2. And then we would be dividing by 0.08. And if we bring our calculator in, we've got the ln of 2 divided by 0.08, and we get 8.7 years, let's say. So 8.7 years. Our second example here is we know that we want to double in 6 years, and we want to know the interest rate. So in this case, we're going to have 2p equals p e to the rt, and t is 6, so 6r power. So when we divide here by p again, we get 2 equals e to the 6r power. Now remember, we could take the log of both sides, but if I show the other method, we're going to convert this to a logarithm function. So this would be log base e. And the 6r and the 2 change places, so we're taking log base e of 2 equals 6r. Now remember, log base e is the same as the ln, and we would be dividing by 6. So the interest rate would need to be, let's calculate here, we've got to calculate ln of 2 divided by 6. And we get a interest rate of 0.116, which would be 11.6%. So again, we're solving exponential equations here to solve for exponents in the compound interest formula.
Are you ready? Are you ready?